Thank you. Welcome to this tutorial that will be about design and characterization of measurement systems based on drones. And it will be held by me, Luca De Vito, and my colleague Francesco Picariello. So, first of all, we have to tell why do we deal with drones. I will tell this with three figures. The first one, we will see that drones are a promising technology because we see the growth of the technology within the years. And the second figure is that first, drones were only done in laboratories and research centers. Then they have been developed for consumer electronics. And now there is the development of the drones for commercial use and for professional use. And that's the reason we deal with within instrumentation and measurement. And the two figures show us what are the main applications of drones. And we can see that among all these applications, most of them deal with monitoring and measurement. Another aspect we have to deal with is that now what is going is that all the reality has been captured. And there is a process for digitizing the physical world by scanning all the things. And the first example of this is Google Maps. Because thanks to Google Maps, a lot of things have been digitized and a lot of businesses grow up thanks to the services of localization and the content that have been provided by Google Maps. About these industries have sought data that are taken from above. And drones are like sensors in the sky, and they are better than satellites or airplanes because they have greater resolution than satellites, and they are safer and cheaper than airplanes. And the quality, reality as captured by drone is now good, and it can compete with laser scanner. I show here an example. Drones have been recently proposed to map, for example, the scene of car accident. And the documentation of car accident is legal issues. And in all cases when there are economic transactions or legal issues, it is fundamental to provide not only the measurement data, but also the uncertainty of the measurement results. If we see the accuracy of this data, we can find on documentation that accuracy is approximately 2 or 5 centimeters, but this is not documented well because there are not structured methods and traceable methods to provide uncertainty. And so let's come to the tutorial scope. The scope is that the drone-based measurement instrument is a complex system for two reasons. The one reason is that it is composed by several subsystems, and all these subsystems like propulsion, flight control, power supply contribute to define the overall system behavior. And the second reason is that the final measurement result is generally obtained by complex indirect methods that operates on data coming from different sensors. We will see later on the next slides. And so the tutorial exposes the designing step for designing a drone-based measurement instrument. In order to design properly and drone-based measurement instrument, we have to look at the main parameters. The main parameters for a drone are, of course, the weight of the drone and the power consumption. And we can see in these two budgets how these parameters are obtained by the different elements. So, for example, for the white, we can see that the main contribution comes from the payload, but there are also significant contributions from the frame and from the motors. Instead, for the power consumption budget, the main contribution is from the motors, of course. And there are also small contributions from the ESCs and also the payload. But we have to also to take into account the uncertainty about this. What about uncertainty? Because all these elements, all the sensors contribute to the uncertainty of the final measurement result. And we have to consider, starting from the target uncertainty of the final measurement result, what are the specifications of each of the sensors which are on board. And then we have to do another budget, which is the uncertainty budget. And this budget will also influence the other two budgets. So after the uncertainty budget, we have also to reconsider the power consumption budget and the white budget. So the onboard sensors must be chosen such that the measurement results complies with the target measurement uncertainty, and specific calibration methods must be defined, applied, and documented also in order to guarantee the measurement traceability. So I have to guarantee that the measurement data I take, it is traceable to international standards. For a drone, this is a little bit complex because, as I told, the drone is a complex instrument in that it takes that data from different sensors and combine all this data in order to produce the final measurement result. So, for example, we can define two types of sensors. We call them sensors for navigations and sensor for mission. Sensor for navigation are all those sensors that are used to estimate the pose of the drone. It means the position and the altitude. And we call sensor for mission those which are the main sensors for the quantity that has been measured. And but we can see that both this type of sensors combine together in order to produce the final measurement results. And so they have to consider both when we evaluate the final uncertainty. Not only this, but in addition to this uncertainty propagation, we have a lot of influence quantities and uncertainty sources that also contribute to the final measurement uncertainty that we have to consider. So temperature, humidity, luminosity conditions, vibrations, magnetic disturbances that act both on the sensor for missions and the sensor for navigation. So in order to define the measurement uncertainty budget, we have to follow the following steps. To identify the uncertainty sources, to evaluate an uncertainty model according to the identified uncertainty sources. We have to conduct an uncertainty sensitivity analysis, and what we will do, what we will have. We will have the feasibility of our system according to the target uncertainty. So we will know if, from a technological point of view, what we want to do, so what is the target uncertainty is effectively feasible. And we will have the definition of the sensor specification, and so what are the set of sensors that we have to use in order to reach that target.
In this second part of the presentation, I will speak about the design steps for implementing a drone-based measurement instrument. The design steps are 6. The first step is the definition of the measurement, the quantities that we need to measure according to the application. The second step is the definition of the target uncertainty and the measurement range. The third one is the uncertainty budget analysis. In that case, we need to evaluate an uncertainty model of the measurement procedure, and according to that uncertainty model, we need to evaluate the sensitivity of the uncertainty sources on the target uncertainty. Fourth step is the definition of the requirements related to the sensor for navigation and sensor formation. After, we have to define the communication link in order to allow the communication between the ground station and the drone. Step is the definition of the drone platform according to the weight budget and the power consumption budget. So, I will apply this design step at photogrammetry for 3D reconstruction. In aerial photogrammetry, the 3D reconstruction is implemented by taking images with the drone in several positions of the object that we need to reconstruct. We use the technique called structure from motion. In this case, the measurements are the geometrical dimensions of the object in the surveyed area, the height, the width, and the length. The target uncertainty in our case, in our specific case, is in the order of 10 centimeters. The higher uncertainty value between these three measurements is due to the high measurement. So we will consider in the analysis only the uncertainty related to the high measurements. The measurement range, of course, depends on the maximum height of the object in the surveyed area. In our case, we have chosen a maximum height of 3 meters. The third step is analysis of the uncertainty sources affecting the height measurements. In particular, we have used a model that is considered for stereo vision measurements. In that case, behind the law of propagation of uncertainty, we can see here the formula related to the uncertainty on the height measurements, which consists of two terms. The first one is related to the recognition of the points that we need to measure the height in both the images acquired by the drone in two waypoints. The second term is related to the stereo vision geometry parameters. In that case, the stereo vision geometry parameters are the distance between the two waypoints where the images have been acquired and the orientation of the second waypoint respect to the first one. In today's uncertainty formula, we have done an analysis of several uncertainty sources affecting the height measurements at several flight altitude. In particular, on the graph, several curves that are a several uncertainty value also for the baseline measurement. From this analysis, we have chosen the maximum uncertainty for the estimation of the distance between the two waypoints, usually called baseline, that should be of 10 centimeters, and the maximum orientation uncertainty that should be of 10 degrees, according to our target uncertainty in the order of 10 centimeters. Of course, we have chosen a flight altitude of 14 meters. After this analysis, we can choose the kind of sensor to be embedded on the drone for the navigation and for the mission. In particular, we needed to measure two quantities, the baseline and the orientation of the second waypoints respect to the first one. In that case, we can use two kinds of techniques. The first one is based on GNSS. For example, if we use the DRTK provided by DJI, we can achieve this uncertainty value. For the baseline measurement, we can achieve an uncertainty value of 1 centimeter. For orientation measurement of 0.2 degree. Or we can use image-based technique where we can measure the baseline and the orientation by recognizing the same features on the two images acquired by drone during the flight. By recognizing that features, we can know the trajectory of the drone during the flight. So between these two techniques, we have chosen the second one for the implementation of our instrument. In that case, the payload will include a camera with a gimbal for the stabilization during the flight, and the sensor for navigation will be a GPS and the inertial navigation system. After that, we need to choose the communication link. In our case, we have chosen as a communication link a communication link based on COFDM, which guarantee a distance between the ground station and the drone of 10 kilometers. The last step is to define the drone bench platform according to the sensor embedded on the payload and the navigation sensor. Here you can see that we have chosen a camera with a gimbal, and according to the weight of these components that will be embedded on the drone, we can choose the number of motors of the drone and the typology of the motor according to the takeoff weight that it can guarantee. In our case, we have chosen a quadrotor and a motor having a takeoff weight of 400 grams for each rotor. After we have analyzed the power consumption of the entire platform, according to that power consumption and according to a desired flight time, in that case is 20 minutes, we have chosen the capacity of the battery that should be embedded on the drone. The cost of this platform is around $1,500 or $2,000, and the estimated uncertainty by using the model that we can achieve is of 16 centimeters. So after the design of the drone, it is very important to characterize the drone platform. In particular, in literature, there are two kinds of characterization. The first one is a characterization performed on test bench. In that case, we need to evaluate the performance of the propulsion subsystem or the performance of the control board. Another kind of characterization is a characterization performed during the flight. In that case, we want to characterize the measurement provided by the drone. So, in that slide, I will show you a characterization performed during the flight of an aerial photogrammetry drone-based measurement instrument. We have chosen as a drone the Phantom 3 by DJI, which complies with the requirements that I have shown before. Here the characterization has been done in order to evaluate the measurement uncertainty. We have driven the drone in order to take images in 16 different positions at 4 different flight altitudes. For each position, we acquire 20 images. And for each couple of images, we have evaluated the height of an object in the chain, which is a box in the chain. The box in the chain. So, here are the results obtained for two used 3D reconstruction tool. The first one is a MATLAB-based 3D reconstruction tool. The second one is a tool available on the market, which is called the Pix4D. In that case, you can see that the uncertainty is in the order of 10 centimeters, so it complies with the target uncertainty that we need to reach. And of course, you can see that at low flight altitude, it seems that the uncertainty for the height measurement is higher than at a higher flight altitude. This is due to the fact that the algorithm that we have used for recognize the trajectory of the drone during the acquisition of the images is confused by details in the background texture. In both cases, in case of Pix4D and in case of the MATLAB-based application, we have seen that the main uncertainty sources affecting the measurements is due to the estimation of the stereo vision geometry parameters. Thank you for your attention.